Grab a phone or laptop charger and look at the tiny print on the back. You will see an input reading of AC and an output reading of DC. DC stands for direct current. This graph maps out exactly what it looks like: a perfectly flat, constant flow of electrons moving in a single, unvarying direction. Because it is incredibly steady, it is highly controllable. That makes it essential for the microscopic transistors in our electronics to function without frying. But that AC input stands for alternating current. Instead of a steady stream, the electrons in this system constantly switch directions, violently jerking back and forth dozens of times a second. If your phone, your laptop, and nearly every sensitive device you own requires a steady stream of direct current to survive, why does the global power grid deliver chaotic, oscillating alternating current right to your wall outlet? That little plastic power brick acts as an active translator, solving a massive physics problem that stretches thousands of miles outside your home. The first commercial electrical grids were championed by Thomas Edison, and they were built entirely on his preferred standard, direct current. Sending electricity from a power plant to a home involves a basic physical hurdle. The copper wires carrying that power have inherent electrical resistance. They physically fight the flow of electrons. When you try to push massive amounts of direct current through miles of wire, that resistance generates extreme friction and heat. Because of this crippling heat loss, Edison's direct current grid experienced massive voltage drops. The power simply burned up in the lines, meaning electricity could only be successfully transmitted a mile or two from the generator. This visualization maps out the exact mathematical solution to that heat loss. To maintain the same amount of total power over long distances without burning up the wires, you have to drastically lower the current and compensate by drastically raising the voltage. Changing the voltage of a direct current system is incredibly difficult and inefficient. That limitation provided the perfect opening for Nikola Tesla to introduce an alternative system. Tesla's alternating current is generated at power plants by spinning giant magnets, which physically push and pull the electrons in alternating directions. The ultimate advantage of alternating current lies in this wavy, fluctuating nature. Because it oscillates, AC can easily pass through a device called a transformer, which instantly steps the voltage up to massive levels while keeping the current whisper-thin. Pumping up the voltage allows this alternating current to travel hundreds of miles across the country with almost zero heat loss. Before that high-voltage power enters your neighborhood, a step-down transformer safely lowers the voltage back to the 120 or 240 volts your wall outlets actually use. Alternating current secured its place as the global standard because it offered a mathematical workaround for wire resistance, allowing humanity to successfully conquer distance. Realizing his direct current system was physically outmatched, Edison resorted to a vicious public relations campaign to convince people that high-voltage AC was uncontrollably deadly. He funded the public electrocution of animals and heavily influenced the invention of the electric chair to permanently associate alternating current with execution. Despite Edison's brutal PR tactics, the undeniable physics of power transmission forced the world to adopt Tesla and Westinghouse's alternating current system for the global grid. The war of the currents ended in a practical compromise. Modern engineering forces a permanent marriage between the two systems. When our devices pull alternating current from the wall, a component called a rectifier flattens the chaotic wave into steady direct current for microchips. Conversely, an inverter chops flat direct current from a solar panel back into a rhythmic alternating wave for standard appliances. Our daily modern lives run entirely on these invisible, constant handoffs between AC and DC power, taking place inside almost every device we own. Look at that laptop charger again. It acts as an active physical treaty, safely bridging the gap between Tesla's massive continent-spanning macrogrid and Edison's DC microworld.